All right, so on the last video, we saw we have a redox reaction. And the last thing I left you with was, what if we make these electrons that are being exchanged here not just be exchanged at the interface, but we make them do some work first. To kind of give you an example here. So in my house, there's a laundry room at the end of a hallway. So it's at the end of the hallway. Let's say my son wants to go work out, and the gym's in the garage. And so he's in the living room, he's saying, hey, I'm gonna go work out. I'm like, okay, that's cool. On your way to the gym, will you please take this laundry, these towels, and go put them in the bathroom along the way? Now, what does he want to do? Where's he being drawn to go do? He's being drawn to go work out. What do I make him do? Since he's going that way anyways, I make him do some work for me along the way. Your parents have all done this to you probably. You say, hey, I'm gonna go to my friend's house. I'm gonna go, my son has a friend named Woody. My son says, hey, I'm gonna go to Woody's house. I'm like, okay, cool, no problem. On your way, since you really wanna go to Woody's house, on your way, would you please stop by Walgreens and pick this up for me? Or will you please stop by the post office and drop this off for me? Basically, long story short, he wants to go to a place, but I make him do some work for me along the way. The thing that's drawing him to it is still there. He still has a draw to get there, but he's being made to do some work. And we can do the same thing with chemistry over here. What we're gonna do is, we're gonna take the copper ions, these copper ions that are pulling these electrons away from the aluminum, and instead of making them do it just at their interface, instead of just saying, hey, here you are, you're instantly teleported to each other, we're gonna make them travel through a wire at first. So let's see what this thing looks like. We're gonna go here. I'm gonna set up a cell. I'm gonna take a container right here, and I'm gonna take another container right here. Okay, so these are just two beakers. What we're gonna do is, I'm gonna fill one of these up with water, another one up with water, and then what we're gonna do is we're gonna consider what the reaction is. The reaction was aluminum plus copper 2 chloride made aluminum chloride plus copper. So let's look at the different species we have. We have ourselves aluminum by itself, metal, copper ions, chlorine ions, aluminum ions, chlorine ions, and copper. We're not worried about balancing right now. So watch this. I'm gonna take right here, all right? I'm gonna take right here, and I'm gonna go ahead and I'm gonna put a piece of metal inside of here. And what I'm gonna do is, I'm gonna put a piece of aluminum inside of this piece of metal, inside of this water right here. Over here, I'm gonna take a piece of copper. I'm gonna put it inside that guy right there. Now, what I'm also gonna do is, inside of the solution, I'm gonna have this guy bathing in its own ions. Sounds gross, but you get the idea. Its own ions, and these chlorides are not gonna be important at all. We're gonna come back to them. In fact, it doesn't even matter what their ions are, so I'm just gonna say A negatives. There's our little A negatives y'all guys love from acid-base equilibrium. Just anions, doesn't matter what they are. As long as they go to the solution, as long as they have a big KSP, we're good. These copper ions, same thing. We're gonna make them bathe inside their own copper ions, and we're gonna have ourselves them inside anions. Basically, it doesn't matter if they're chlorines or whatnot. If this is copper nitrate and aluminum nitrate, or aluminum chloride and copper nitrate, the whole reaction is going to be the same. Those are not important. The reaction took place between the aluminum and the copper ions. The chlorines are just there along for the ride. Plain and simple. You have a date, you bring the date, you and some other person have a great conversation, your date just kind of disappears. It doesn't matter if you bring Sally or you bring Sarah. It doesn't matter. The actual reaction is between you and the person you talk to. So we come back over here. We know that these copper ions and this aluminum here can have a relationship. So what I'm going to do is I'm going to connect from here to here a wire, a metal wire. Now, if you remember what metals are those nuclei with loose held on electrons being able to freely move around. And so when new electrons come in, they push the electrons in the middle along the way. And so we're able to get that conductivity of electricity. So now we come over here. What's going to happen? The copper positive 2's reduction potential, its potential to get reduced, is going to pull on aluminum's electrons. It's going to pull on them. And those electrons are going to begin to flow. The electrons are going to begin to flow down, 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 down into the copper ion solution. What's going to happen now is exactly what we just did a second ago. Those copper ions are going to begin to gain the electrons and become copper. They're going to become copper. And what's going to happen is this, what we're going to say an electrode, this electrode here, and specifically we're going to say this cathode. Why a cathode? A cathode is the source where reduction is taking place. This is where reduction is taking place. You can always remember red cat. All right, so red cathode, reduction cathode. So this anode, this electrode, called a cathode specifically. So remember, ions have cations and anions. Well, electrodes, which is this metal rod here, is a cathode. Okay, now this copper ions are going to begin to gain the electrons. Okay, great. Over here, this aluminum is going to begin to lose electrons. So what's going to happen now is we're going to start depositing aluminum ions inside of this solution here. So now we go back and say, well, what's going to happen then to this electrode over time? What's going to happen to this electrode over time? Over time, this electrode is going to begin to dwindle down in size. Well, then vice versa, what's going to happen over here to this electrode? Well, we're forming more coppers. Those coppers are going to start attracting to the metal. And when they hit the metal, that metallic bonding, that electron C comes in. And we're going to start getting a fattening up. We're going to start getting a fattening up of this with copper. Now, with that being said, what is actually happening? What is taking place? Now, we're missing a salt bridge. We're going to come back to that in a sec. What is actually happening? These electrons, as they travel down this wire, we can put them on what we're going to call a load. Now, what is a load? All right, so we have something here. It's a light bulb. That's a light bulb. We're going to have the electrons travel, and instead of going straight through, they're going to come up into a wire here, and then out of this wire. And this wire right here might be something of higher resistance. In physics, you learn about a thing called resistance measured in ohms. And basically what you can think of is that the electrons are going to begin to slow down. They're going to slow down. And when they slow down, they start creating more and more rubbing of electron to electron rubbage. And what that causes, it causes friction. You take your hands and go like this. You start creating friction. Friction creates heat. Heat creates black body radiation. What is that? We get ourselves this nichrome wire in here will begin to glow. And then they're going to keep moving along the way to where they eventually want to go. Just like if I send my kid to Woody's house and I say, stop at Walgreens, he's like, I can just get there. Why can't I just get there? Well, I'm sorry, you got to stop by, take out 15 minutes of your time. It's going to cause some friction, I guess, and you're going to hang out and do a chore for me first, and then you can go along your way. So what ends up happening is those electrons, as they travel, will create a heat. They'll create a ability to do some work for me. So they're able to create some energy. Energy's ability to cause change. Energy is measured in joules. So we have some joules on here. And in fact, what we say is this ability to pull the electrons this way, we say is measured in voltage. Voltage. And voltage, imagine, is it's the potential to pull, it's the potential for energy on a charge. It's a potential for energy on a charge. Imagine if I take two magnets, and those magnets were extremely strong, and I bring them closer and closer and closer to each other, and then I put your hand between them. Their ability to cause change on your hand is going to be directly proportional to how strong their attractions are to each other. Imagine if the magnets were really weak, their ability to pull onto each other and smash your hand, not very strong, not very strong. And don't do that. Neodymium batteries will actually shatter your bones, so be careful. Voltage is measured in joules per, we're going to come back to this, coulomb. Joules per coulomb. If you remember Coulomb's law said that the attractive forces between two charges, Q1, Q2 over R squared, is directly proportional to the charge differences, positive and negative charges, divided by the radius, so how far apart they are from each other. Well, so what do we have? Voltage is equal to joules per coulomb. So the greater difference between these aluminums pulling down and these coppers pulling down give us a volts. A volts, a potential to pull electrons this way. We're going to come back to a second video.